All right, we seem to be set up, so let's slowly get into it after lunch break here. All right, so this session is a sort of continuation of the storyline of the keynote, but not really. It actually covers Spring Framework 5 and the current state of affairs from a slightly different perspective. I admit this is a quite personal selection of topics. I'm going to talk about the things that I personally care about in Spring Framework 5, topics of immediate design relevance, of immediate relevance for how you would choose a configuration format, choose your programming model. But I'm also going to cover some other ground. So it's going to be a little bit of functional API style. It's going to be quite a bit of reactive web architectures in here. But it's also other stuff that we usually don't talk about. These are the hidden gems. So I'm also going to take some time in kind of the third part of this presentation to just highlight a few things that I find important or interesting that are not usually covered in other presentations that we're doing. All right. Well, for Spring Framework 5 itself, this is kind of the fact sheet, right? Let's take it for what it is. A Spring Framework 5.0 is the current generation. 5.1 is what we're working towards. I'm mostly covering 5.0 because 5.1 is a sort of minor upgrade for JDK 11 compatibility purposes in particular. Very importantly, the opportunity for Spring Framework 5 was to revisit the entire code base, right? Raising the baseline to Java 8+, bringing Kotlin support, Kotlin extensions into our code base was an opportunity to literally touch almost every source file in the framework's code base. We don't do that too often. We did it for 4.0. We did it once again for 5.0. And I'm going to highlight a few of the things we did to the code base in the course of this presentation. So all the baselining aside, it's basically the usual stuff, right? We expect reasonably recent versions of the JDK and the servlet containers underneath the covers. And we're also not only compatible with JDK 9, but JDK 10 at this point, and with the current crop of servlet containers. So servlet 4.0 that would be Tomcat 9, for example, Undertow 2. So we're basically exactly where the infrastructure is what we're covering. But let's move away from all this baselining a little and spend a little bit of extra time talking about the component style. Which kind of was a topic that went through those 15 years this morning. We traditionally have a strong focus, or at least in recent years, we have a strong focus on annotation-based components, as I'm sure you're well aware of. So Spring is oftentimes perceived as an annotation-based framework these days. That was never actually accurate. So the Spring as a framework, both in the core container and in the web stack, is actually not annotation-based, and it never was annotation-based. The annotation-based component model is kind of sitting on top, adapted to the actual inner workings of the Spring framework underneath the covers. The framework facilities are designed in a totally traditional mindset, basically classic object orientation at work. API interfaces, SPI interfaces, inheritance arrangements in a few cases. In Spring Framework 5, we're making plenty of use of modern-day Java, so you'll find interfaces with default methods and whatever else, but it's actually a pretty traditional, very classic Java object-oriented design at work there. And the annotation-based story sits on top of that. So what we did for Spring Framework 5 is to take a step back. We have this well-established, comprehensive annotation-based component model. We spent lots of time on it in Spring Framework 3 and following, in 4, 4.0, 4.1, 4.2, 4.3. They were all refining the annotation-based component model. But for 5, we're taking that step back. kind of revisiting what the framework is actually doing, the actual purposes that the framework is serving. The annotation-based story is in place, but what about configuring and instructing the framework, once again, from a programmatic perspective? Programmatic on Java 8 and higher, programmatic in a functional style, as in Java util functional and Java 8's functional language features. What about bringing a new language into the picture? First-class support for Kotlin out of the box, what would that really mean? What are the idiomatic ways of expressing yourself in Kotlin when interacting with a framework like Spring? So this was a quite interesting design challenge, making the framework internally ready for a functional style interaction model. It was actually quite ready already, right? It's not like we had to rip out anything, because not using annotations with Spring means simply not activating the annotation processing. Then you have the bare bones object-oriented framework underneath. What we did for Spring Framework 5 is to make it more convenient than that, to introduce specifically crafted methods, specifically crafted API for functional registration purposes. We kind of optimized programmatic usage of the container, you could argue. This sounds straightforward, but even from where we were, there was plenty of stuff to do. Kotlin extensions all across the code base is one thing. Having Java 8 style support for callback interfaces, for Lambda expressions, method references, use of Java util functional interfaces in our method signatures is another thing. But there's more to it. In a functional style architecture, we took a rather extreme position, right? Functional as in purely programmatic. No annotation support active at all, so no annotations in use. No class path scanning, God forbid, right? Everything needs to be explicitly registered, very traditionally programmatic. Let's avoid class path scanning. And let's even go as far as avoiding reflection. So no runtime reflection into user components, ideally. All of this, of course, is a rather extreme position. We're basically saying no annotations, no class path scanning, no reflection. We, of course, know, we are aware that in practice, that is an extreme position, that the middle ground is actually pretty interesting. You might use a little bit of reflection. You might combine functional registration with class path scanning. You might want to activate annotation support and combine it with functional registration. All of this is, of course, very worthwhile on its own. But from a framework design perspective, it is an interesting challenge to take a more extreme and more pure perspective and try to make the framework usable even under these more extreme restrictions. So what does this mean in practice? And I've been showing the examples. This morning I'd like to just highlight a few details here at this opportunity. This is actually kind of what came out of it. We didn't want to overdo it and introduce too many variants of doing the same thing. Just add a few very specifically crafted methods that really serve quite a few purposes. So I've already elaborated a little this morning that in these examples there's a few hints on what you can customize. This is basically the simple version. If you just register a class, we have to apply default conventions. We have to kind of do default instantiation. If you specify an instance supplier, then the framework knows how to create an instance of your class. So it will never try to call a default constructor. It will always call this instance supplier, which is typically a Lambda expression or can be a Java 8 method reference. If you want to go further, there's these bean definition customizers. There can be any number of those because it's a var arc. So if you have several things to customize, you could either use a code block or you could stylistically just have one more bean definition customizer, one more Lambda expression in line. So it's actually quite straightforward in what you do here. It's very close to the inner workings of the Spring container. But we did bake it right there into the core. So the core container actually has support for instance suppliers at its very lowest level. We're not trying to reflectively call this instance supplier. We are dispatching straight to this supplier, which at runtime means basically an invoke dynamic call to the lambda expression representation in your class. There's literally no reflection involved. So if you're using this variant with instance suppliers, there's no reflection. If you're just specifying a class, you're technically asking for class.newInstance, right? This is not what we're actually using because on JDK 9 that's deprecated, but it's very similar to what we're doing. It's effectively, we're using reflection to call the default constructor. Now, where's the difference here? This is a Java 8 method reference, referencing the default constructor of foo. Foo : new is basically just a reference to the default constructor. The idea here is, the trick here is, that this is an instance supplier. So it's a method reference compiled to an instance supplier. It's effectively equivalent to a lambda expression like this one here. So we are not using reflection. We are dispatching straight to the default constructor of foo through an invoke dynamic instruction in the bytecode. So this version of the example below here with foo new involved does literally not use any reflection at any point. So that is the sort of more extreme position. In practice, would you do this? Only if you really care about saving every single CPU cycle. Probably not for singletons anyway. So in practice, this is all good enough, right? We're just trying to make it possible for specific purposes, for specific services running in a highly dynamic cloud environment, where after 15 seconds it's torn down and then spun up again if some new requests come in. For specific purposes and constraints, we wanted to allow you to squeeze every potential optimization out of your setup here. I've also quickly been showing the Kotlin example this morning. This is also worth a little bit of elaboration. What I'm calling Java style up here is effectively a name that I made up. There is no Java style and Gradle style in Kotlin. Those are names that just I'm using or that we are using to explain things. Those are not official names. We are dubbing this the Java style simply because it is quite similar to the Java equivalent, right? Structurally, this is very close to what we've seen before. We register foo.class, default instantiation. We register a bar instance, but we are only specifying one Kotlin function, no extra argument, right? We're not saying bar.class and here's the lambda expression for the supplier. We are just specifying the Kotlin function. So effectively, this is using an overloaded method from a Kotlin extension on generic application context extensions.kt that we internally ship. So from a Kotlin perspective, this is not a lambda expression, it's an actual K function, a Kotlin function. And the Kotlin reflection API allows us to reliably infer the return type of a Kotlin function. Whereas in Java, such a lambda expression basically does not have a runtime inferable return type. From a framework perspective, we do not know that this is producing a bar instance. It can't produce anything, it's basically an object. We don't know what's coming out of this. And there's no reliable way of inferring it in Java compilation. The Kotlin compiler, when compiling a Kotlin function, explicitly stores metadata for those functions in the bytecode and allows us to reliably infer that this function produces a bar instance. So there's no need for an extra bar.class argument. It's as simple as that. Makes it more convenient, of course. You're not repeating yourself through an extra argument. What I'm calling the Gradle style usage of Kotlin here. A Gradle style just means similar in style to the Gradle DSL. The Gradle build tool traditionally has a Groovy specific configuration language. There is a Kotlin configuration language as well for Gradle, and this is using Kotlin in a similar way to here. basically instantiating the application context, but then not calling this outer reference using nested method calls on this scope. So it's effectively like calling ctx.registerbean, and using generic specification. So like an inline generic type for the type arguments, which is a clever spin in the Kotlin language. Once again, it's the Kotlin compiler at work here, and it retains information. There's no type erasure here. We have runtime retention of this type information, and we can infer it at runtime. So it's effectively equivalent to the syntax up here. But language-wise, you're not specifying an argument, or even here, you're not specifying an argument. You're basically using generics, Kotlin generics, in a clever way. Whether you prefer this kind of style or this style is up to you, right? Our Kotlin extensions are basically just a set of methods that allow you to use Kotlin in these ways. Personally, I'm trained in the Java mindset, so I find this still quite nice, the Java style. But of course, this is quite nice if you want a more DSL-like experience. And it even goes a little bit further. So we even have a beans and bean DSL style arrangement in Spring Boot 2. If you're using Spring Boot 2 with the Kotlin starter, in the startup class, you can even use a sort of DSL style beans arrangement, which is even more DSL-like in Kotlin. So Kotlin gives you quite a few variants of registering beans in convenient ways. All right, so much for components, the component style. Reactive architectures are, of course, kind of the central topic in Spring Framework 5, and to quite some degree also in Spring Boot 2. So let me elaborate on the inner workings a bit. We have reactive streams at work here, and reactive streams underneath the covers is just a very minimal abstraction between a publisher, a subscriber, and a subscription that kind of ties them together. It's essentially a model for flow control. So at the heart of reactive streams, you're basically interacting with kind of hot I/O streams in a very dynamic fashion. You put the subscriber into the driver's seat. So the subscriber basically kicks it off. Registering a subscription against the publisher kind of makes things happen once the subscriber starts consuming elements. It basically requests the next number of elements from the publisher, which actually triggers publication, right? The publisher does not do any work before a subscriber starts asking for it. If a subscriber suffers from network congestion, if it's trying to write to an HTTP response stream and the network is currently overloaded, right? You basically, the local buffer is full and it can't write any further data without blocking, then the subscriber is not going to take further elements from the publisher. So in both ways, it's always the subscriber in charge. The publisher does not overload the subscriber. It only publishes the requested number of elements. Which might not be any elements at all, so the publisher doesn't do anything until the subscriber is ready to begin with. This is the inner workings, basically. You're not coding at that level. This abstraction is primarily relevant for people building reactive HTTP engines, reactive data store drivers, reactive web clients. Basically, it's an infrastructure level interaction model. What we did in Spring Framework 5 is actually up here. Kind of this part here is basically the user level component model, right? You building the endpoint methods, the endpoint types. This is the component model level for application purposes. Underneath the covers, in the traditional Spring MVC stack, Spring on servlets, there is, of course, the traditional servlet assumptions at work. So we are very intentionally trying to expose the servlet nature of the underlying stack. Literally, up here in a controller method in Spring MVC, you could declare an HTTP servlet request argument or a HTTP session argument because you know that your controller runs on top of the servlet stack. But it's not just that. You know that you're running within a servlet container dispatch. So there's a thread from the servlet container's thread pool attached to you. Your handler method receives the request within such an assigned thread and is able to process the entire request, even write the entire response, and then return. That's essentially the servlet model, a sort of imperative programming model for handling HTTP requests. There may be many blocking operations involved, and it doesn't matter because you've got a thread of your own. You're perfectly able to block that thread, waiting for a JDBC call to return, a JPA call to return, a REST template call to some other microservice to return. This is all easily doable because all you own is one of many threads in the servlet container's thread pool. Under regular conditions, that's perfectly good enough. It just starts having issues under really high or really uneven load where you may possibly exhaust your thread pool. If the servlet container does not have any threads left in its thread pool, well, then it starts rejecting requests. So any newly incoming HTTP requests, even ones for index HTML, are going to be rejected because there's no thread available to handle them. I mean, of course, you can fine-tune how it actually will behave under those conditions, but there is a limit to what it can handle at runtime. In a reactive architecture, as introduced in Spring Framework 5 as the Spring Web Flux framework, which is basically a parallel web stack living next to the servlet stack, but being designed with a different foundation. A sort of similar programming model on top, but a very different foundation underneath the covers. What we have here is reactive streams at work. And in its pure incarnation with the Webflux server stack, there's an event loop here. The event loop, of course, is a sort of thread pool, right? But only with as many threads as you have CPU cores, essentially. So for 16 CPU cores, 16 threads. Basically the actual concurrency level that your hardware is able to handle. In terms of incoming requests interacting with that event loop, they are not directly ever owning a thread. There's always a callback triggered from the event loop, the next step in your processing pipeline. It's never blocking, so it needs to be non-blocking all the way down and back up. No blocking stream interaction anywhere. So anytime your event loop actually dispatches to one of the next steps in the pipeline, it actually keeps a CPU core busy. So we're never ever making the CPU wait on anything. It's non-blocking for a purpose, for maximizing the use of your actual hardware resources underneath the covers, both at the CPU level and at the networking level. So the stack options or the provider options, engine options underneath the covers here are also worth a note. In the Spring MVC world, you traditionally choose a servlet container, right? Very commonly used, that would be Tomcat or Chatty or Undertow, which is the HTTP engine underneath Wildfly. It's available as a standalone product and also supported in Spring Boot. And of course, the traditional application servers, you could run it on WebLogic or WebSphere or a full Wildfly arrangement. Over here, it's a little different. There's a reactive streams-based abstraction here, no servlet API. There's no servlet API leaking through here. Up here, you cannot consume any servlet artifacts. You cannot rely on any servlet semantics. Down here, there are basically two kinds of options. One of them is not a kind, it's just Netty, right? The most powerful networking stack on the JVM available. Making our reactive stream story work on Netty was, of course, a key design goal. So that's an ideal combination and the default in Spring Boot 2 for that reason. Alternatively, you may also use other reactively enabled HTTP engines underneath here. It's an abstraction after all. And you can choose to use Tomcat or Chatty or Undertow over here as well. But you're not using them as servlet containers. You're using them as reactive HTTP engines. Because at the heart of Tomcat and Chatty and Undertow, They are HTTP engines, right? Basically networking stacks. Putting servlets on top is one way of using them. You can also adapt them to reactive stream semantics, and that's exactly what we're doing here. So they may be servlet containers in most scenarios, but down here, they're not actually servlet containers. They are HTTP engines that we are adapting to the reactive web abstraction. And this actually works quite nicely. So the Webflux stack on Tomcat works perfectly fine. It has, of course, been worked on. We have a dedicated person on the Tomcat team. We actually have 3 full-time engineers on Tomcat at Pivotal. One of them primarily focuses on improving Tomcat's usability in reactive stacks. So this is a dedicated working area where lots of optimizations are also done for Tomcat and for Jetty themselves. And for Undertow, it's even better. The Undertow project has an Undertow core and an Undertow servlet level. Of course, over here, you need Undertow servlet. Over here, all you need is Undertow core. So that separation is actually cleaner in Undertow than in Tomcat and in Jetty. So Undertow is also perfectly usable over here. In another kind of diagram, Spring MVC and Spring Webflux, WebMVC and Webflux actually share quite a few things, and they differ on quite a few things. You can use an annotation-based controller model in both of them. But if you want to do imperative logic, handling a request with blocking JDBC or JPA calls over here, any other kind of blocking APIs like REST template or others, if you want to code like this, you're certainly better off on Spring MVC and on servlet stacks in general. Whereas if you happen to interact with a data store, and that data store has a reactive driver, a reactive streams-enabled driver ideally, like Redis, like MongoDB, like Couchbase and Cassandra, by all means, take that reactive power that the data store driver gives you, try to expose it throughout the web stack, up to the HTTP endpoints, and back down again. So this is essentially what Webflux is for. If you have a reactive API that you can use, expose its power to your web endpoints. So from a simple bottom-up perspective, if you use blocking data store APIs, choose Spring MVC on the servlet stack. If you have reactive data store APIs, or if you're building a microservice arrangement and you have reactive web clients that talk to other microservices, try the Webflux stack instead. Netty is only available over here, as per the previous discussion. Tomcat, Jetty, and Undertow can be used as servlet containers for Spring MVC stacks, or as reactive HTTP engines for Webflux stacks. And there's a nice little middle ground for reactive web clients as well. If you only need a little bit of reactiveness for certain endpoints, you can even use reactive endpoints on a servlet container. I'll elaborate on that a bit in a moment. Let's revisit the actual programming model first. So this kind of controller looks like a Spring MVC controller, but if you look a little bit more closely, the handler methods are actually returning a reactive streams publisher. Not a raw publisher, they actually return a reactor mono or a reactor flux. Both of them are publishers in terms of the implementation hierarchy. Mono is a reactive streams publisher for a single element or no element at all. And flux is essentially a stream of elements. So it's a little bit like Java util optional and Java util stream. Or in RxJava, this would be an RxJava single and this would be an RxJava flowable. Side note, you can actually use RxJava here, but let's focus on reactor for our purposes. So these methods are a little bit different in their purpose. Instead of taking a request and having a servlet thread and producing the response within the body of the method, that's not what we're doing here. It's a different purpose. We're going to get an invocation from the dispatcher if a corresponding request comes in. This getUser method is going to be called. We have the same flexibility in terms of the method signature that we know from Spring MVC. So you can extract path variables and query parameters and request headers and whatever else you need here, in particular from the header. Then your body of the method builds a reactive streams publisher that is able to produce the response. It is not actually doing any work yet. It's just a pipeline that can produce the response once triggered. So it's basically a sequence of steps. And that's what you're returning. So at runtime, the request comes in. We call this method. The method just spends a few CPU cycles building those objects and immediately returning. So we have a handle. We know that, okay, once the request is ready to be fully read, once the response stream is ready to be produced, we can actually dispatch to, we can actually call, trigger this reactive streams publisher. In reactive streams terminology, we are registering a subscriber, right? We are creating a subscriber for the HTTP response. We are attaching that subscriber to the publisher that you're returning here, and then reactive streams does its magic. As the response stream can be written, the subscriber asks for the next elements from the publisher. It's going to send them through a reactive codec arrangement and write them out to the HTTP response. The runtime system handles it for you. All you need to do here is return a publisher that actually does the work once everything is ready. And in these simple cases, we are calling Spring data repositories. You could also have a custom repository that you crafted. You should interact with other APIs that are capable of producing reactive streams publishers here. So this is the annotation-based model. This is a variant of a functional registration model that basically does the same thing. And it's quite self-explanatory if you look at the signatures here, but it comes from a different design mindset. We're basically expressing the same logic through router functions and handler functions. There's an incoming request matching a predicate. There's actually a predicate abstraction underneath here. This comes in from static imports, in case you're wondering. This is Java, but it's static imports. And we're passing in a handler function through a Java 8 method reference. So we are saying, I need a handler function, derive it from this signature here, please. And for the other request, for /users, pass control to this handler function. Like in the annotation-based model for reactive streams endpoints, we are returning a reactive streams publisher. It's a little more explicit here. There's a server request coming in and a publisher for a server response going out. No flexible signatures because we adapt to the handler function signature, and it looks like this: server request in, server response out. So we can't use add path variable. We can't use any annotations here at all. So we have to programmatically interact with the server request, asking it to extract the path variable by name, convert it to a long. In this simple case here, it's a little simplified, and then pass the outcome of that conversion into the repository find by ID method. It's kind of a functional style interaction chain, somewhat similar to Java util collection streams, or to, in particular, very similar to Irish Java logic, and serving the same purpose as this little method here. So it's a little more explicit, but there's no annotations and no reflection involved, and a lot of programmatic flexibility. Then we build a server response, HTTP status OK, and here's the body, the publisher for the body. So there's also a clear separation. Here's the server response, which also has headers, and for the body of the response, take this publisher for a user and send it through the codec chain. So by default, for a there's content negotiation. If we are supposed to produce JSON, we're going to send it through a checksum codec. If we're supposed to produce XML, we're sending it through an AALTO codec. Basically, asynchronous, reactively enabled codecs for JSON and XML. Here for the other endpoint, it's even simpler because there's no parameters to handle. So we're just calling the repository, building the actual response programmatically and returning. In its slightly different variant on this slide. This is exactly the same code using a different Java language arrangement. You might find it a little more pleasing to the eye. There is no handler function signature that you're seeing because we're using embedded lambda expressions. Not method references, but lambda expressions. We're saying for a predicate that matches this, here's the handler function, request coming in, server response going out. And for that other predicate, there's this other handler function. The handler function signature is nowhere to be seen according to Java 8 language conventions for nested lambdas. So this is basically the programmatic equivalent of the annotation-based component that we're seeing here. These are all ways of tying a reactive streams publisher to a particular web endpoint, potentially transforming its content, its object, potentially enriching it with headers and everything else that needs to be in the response. That's the purpose of those endpoint methods. And in the annotation-based model, these endpoints can even run on Spring MVC to some degree. This is a programming model element in our web programming model. If you choose to have endpoints like these in Spring MVC on the servlet stack, then we're not running in an event loop environment, but we know how to handle them. We know, okay, we're actually on a servlet environment, but your code gave us a reactive streams publisher. So we're doing the best we can to translate that publisher onto a servlet response. So if you put this kind of code here, if you deploy it to dispatcher servlet on Spring MVC on a standard servlet container, what we're going to do is we're going to take this publisher that your method gives us. We are switching the servlet response into async mode. And then we're using servlet 3.1 async IO streams to take your publisher and do a little bit of back pressure, interact with the response that way. We're essentially adapting the servlet response to reactive streams, doing the best we can to produce the response in the way that you presented it to us. So it's a kind of best effort adaptation of reactive streams to the servlet stack. That works as well. If all your endpoints are reactive streams based, then you're better off on an actual Webflux server, like on Netty, with a pure event loop setup. But if you have many endpoints, most of which are traditional servlet endpoints, only some of which are reactive streams enabled, then you can choose to combine them in the same application on a servlet stack. So our reactive support in Spring 5 is actually quite flexible. All right, these styles are exclusive to Webflux, so to the event loop-based setup, and to a pure reactive stream server. And last but not least, here's an indication for what a web client can look like. We have a similarly designed web client API. This is basically an alternative to REST template, interacting over HTTP, interacting with other services, and producing a reactive streams publisher. So instead of REST template, which is essentially blocking and waiting until the response returns, here we actually build a reactive streams publisher. And these publishers can easily be integrated into code like this, right? If you have an incoming request on a reactive streams stack and you want to forward the request to some other service, transform the response a bit and return it from here, then our new web client API is your friend. Of course, you can also choose to just use the client API, right? Or you can choose to use this web client API for a few servlet endpoints in your servlet architecture. You can combine those things as they make sense for your purposes and as you are technically able to set up the infrastructure for it. All right. So for the remaining few minutes, I'd like to mention a few further things that we have been doing in Spring Framework 5 that are often overlooked because of all the reactive story and the Java 8 story, Java 8 and 9 story. So a few things in a quick rundown. All over the code base in Spring Framework 5, you're going to find nullability annotations now. Spring's entire API surface, even down to the very internals, uses a not null by default convention now. So any incoming parameters are supposed to be not null by default. returned values, outgoing values from a method call are also not null by default, and even internal fields are not null by default. If something is actually nullable, if a parameter may be null, if a return value may be null, or a field may be null, then you'll find explicit at nullable annotations on those artifacts now, all across the code base. The primary reason why we're doing this is Kotlin, because Kotlin makes use of nullability declarations for Kotlin compiler assignments. Basically, if you're in a piece of Kotlin code, if you're calling, say, beanfactory.getBean or any other Spring API, where you know that the outcome is never null, then the Kotlin compiler allows you to assign it to a non-null variable declaration, to a non-null type declaration. Kotlin, in the Kotlin language, you have a very explicit support for nullability. These annotations in our code base make the Spring APIs a good citizen in that kind of world. The Kotlin compiler makes good use of that information, of that meta information. It's also quite useful for Java. In Java, it's primarily documentation. You can look into the source code or look into the Java doc, and there's a formal declaration whether this thing can be null or not, right? It's not just some words in the Java doc that may be accurate or not. It's an actual formal part of the method signature now. So yeah, I find it also of great value for those documentation purposes. And we actually validate this with, in IntelliJ IDEA, with the constant conditions and exceptions inspection. So you can use this in your code as well. We are using it for the framework itself to validate that our nullability declarations actually match the implementation logic. So if you use that kind of inspection in your code, IntelliJ IDEA understands our nullability declarations, so you get proper validation of your calls into our APIs. Along the same line and at the same time a little different, let's take the object provider API. That's actually a variant of an injection point, basically a flexible way to retrieve instances for a bean that you were asking for. If you look at those signatures in Spring Framework 5, you'll find that the traditional methods, like getIfAvailable, getIfUnique, they're actually marked as nullable now, because getIfAvailable means you get the instance, but if it's not available, you get null, right? This is very explicit now in Spring Framework 5, annotated with at nullable. At the same time, we provided alternative methods like getIfAvailable with a default supplier. That's a Java util function supplier. The outcome of this is not nullable, which is also formally obvious now, because if it's not available, we're going to call the default supplier, produce this default instance. Or even more functional, if available and the Java util function consumer, right? If this other instance is available, an instance of this other bean is available, call the consumer, otherwise skip that step. So we have a few new, those methods are new in 5.0, allowing you nicer programmatic, functionally styled ways of interacting with the dependency injection model. We have support for data class binding now. What does that mean? In all brevity, again, it's Kotlin as an inspiration. If a Spring data binder, like in Spring MVC, a method argument, is in charge of binding incoming parameter values onto a target class, it's now a bit smarter than before. Previously, we always expected setters. We believe that these are mutable objects, right? What if the object is actually immutable? What if the data class doesn't have setters? It only has a constructor with named arguments accepting the state of that data class. Well, as of Spring Framework 5, we auto-detect that. We look at the class. If it doesn't have a default constructor, we evaluate it as a data class. Does it have a single primary constructor? Then we look at the names of those parameters, resolve them from the incoming parameters, and create an instance that way. This is a particularly nice fit for Kotlin data classes like this one. This is a full Kotlin data class, a one-liner. It also works with the same convention in regular Java code. Or it works with Lombok, because Lombok has actually an add data model that works very similarly. It creates a very similar kind of class. If you hand code it in Java, create the fields, a single constructor, final fields, assign the fields, add some getters, add equals, add hash code, add toString, and you basically have the same kind of class. And our data binding natively understands those classes now. In all the reactiveness that we're talking about, we often forget to mention that we also improve the async scheduling facilities underneath. In the core container for many years already comes with a task executor and task scheduler abstractions. Those have seen an overhaul in 5.0 as well. There's direct adaptations for completable future. There's scheduling methods that take Java time instances and durations as argument now. And most importantly, there's monitoring for both of them now on a couple of facilities. This shows up as the new scheduled task actuator in Spring Boot 2.0. So even if you're not using reactive pipelines, but you're using traditional asynchronous scheduling, even then you get improvements in Spring Framework 5 and Spring Boot 2. Well, as a kind of minor detail, the resource abstraction is now capable of NIO2. It's using NIO2 internally, and it has new methods. Instead of input stream and output stream, you can use readable channels and writable channels now without doing any adaptation. So with native support in Spring's resource abstraction, which also goes really nicely with highly optimized asynchronous or reactive web stacks that need to interact with some underlying resources. A sort of side note, if you ever had an issue with component scanning in a traditional annotation-based setup in particular, then maybe check out a new feature in Spring Framework 5 called the Components Indexer. The Components Indexer is essentially a build time task, an annotation processor that you just attach to your build, and it's going to generate a little spring.components file that's to be included in your jar files. And at runtime, when you instruct Spring to do a component scan, we are not doing a full scan. We look at the spring.components files, listing a few class names, and we're only going to look at those classes listed in the Spring Components file, because we know that only those are annotated. We can ignore all the unrelated classes. So this is a nice little optimization if startup time is an issue. It's not necessarily much faster than a regular component scan, but in specific environments like on Google App Engine or in a JVM Security Manager environment, against network file systems, where basically I/O is slow. That's where the components indexer may deliver some value, in particular for cloud deployments, for deployment units that are started and stopped frequently. So, last but not least, we finally revisited our logging arrangement, but only mildly. Spring is still internally using the commons logging abstraction, but we ship a commons logging bridge now out of the box. So if you look at the POM dependencies, in particular in Spring Boot 2, there is no bridge anymore, no external bridge. There's the Spring JCL jar, and Spring's commons logging needs go through Spring JCL. Spring JCL auto-detects log4j2, SLF4j, and falls back to Java util logging. So there's no need for manual excludes in your POMs, manual includes of the SLF4j, the JCL over SLF4j bridge. None of this is necessary. Take the Spring jars, add log4j2 or add logback, that's all you need to do. Everything else should flow smoothly without any extra customizations in your POMs. That is our backwards compatible and at the same time hopefully convenient way of handling the mess that is logging in Java. All right, so much for what I have for you this afternoon. So remember, Spring Framework 5 is already out. In 5.05, it's actually prepared for JDK 10. It does everything we've been talking about in this presentation. And we have Spring Framework 5.1 upcoming for a GA release in September, release candidate 1 in July. With the primary target is tracking JDK 11, this next long-term support release of the JDK, which is also due in September. We are doing a few infrastructure upgrades. We upgraded our CGLib fork. We have ASM 6.1, actually 6.2 soon coming up. We have a new generation of Project Reactor. Project Reactor is where Flux and Mono come from. It's at the heart of our Webflux stack. There's a new generation of that waiting for us. And last but not least, there's also Hibernate ORM finally has a 5.3 release, actually a pretty major 5.3 release that we're also going to have full and comprehensive support for in Spring Framework 5.1. This is what is coming your way in just a few months. All right, so thanks for your attention. Quick reminder, there's a BOF session tonight, I believe actually in this room at 7 p.m. as an opportunity to discuss everything I've been talking about today, or also everything I've not been talking about that you're still interested in and around Spring. There will be 3 of us on stage there, in particular Josh Long, who will do tomorrow's beautiful Kotlin keynote. So join us for the BOF at 7 p.m. if you have any further desires to discuss things. So thanks for your attention so far. Enjoy the rest of the afternoon.